lectures to be delivered by Rob Myers today, tomorrow, and the after. We also have a special ICT-SISC joint colloquium by Barry Sanders tomorrow. So the format of this discussion meeting will be, there'll be several speakers giving 1-hour talks. And since it is a discussion meeting, we encourage you to ask lots of questions. So the first speaker for today is Gautam Mandal from TIFR, who's going to talk about long-time behavior of reduced density matrices in 2D quantum quench with conserved charges.
Thank you. Thanks for the invitation to this meeting. It's always great to be here. Okay, so that's quite a mouthful of a title. So I'll start with the motivation, what exactly we're trying to. So some part of this will be a computer presentation. After that, when the details come, I'll go to the blackboard. So we know that equilibrium physics, of course, has a lot of universality. Namely, if you tinker around with the system a little bit, okay, there are some robust features, and you can describe the system rather nicely by thermodynamic quantities, the entropy, temperature, free energy, and so on. And this has sort of taken almost like 1/2 of the last century to figure out about the universality classes of equilibrium phenomena. So universality in non-equilibrium, of course, is is more difficult. So I have mentioned just one review here for people who are interested, but then there are many others. So for example, one of the questions, can time-dependent behavior also be described in terms of a few robust parameters? There is also this interesting question of whether there is an equivalent of a free energy or an entropy for non-equilibrium phenomena. And if there are such parameters, how are they related to equilibrium properties, assuming that an equilibrium exists? And the question about whether an equilibrium exists, that of course is also very important. Okay, so the advent of ADS-CFT has made this question even more interesting, because for example, equilibrium properties are described by black holes, and therefore at least the long time behavior in systems where there is equilibration, it would make sense to try to see the universalities of gravitational collapse geometries. So this is the one in which you send in null shell. It could be infinitesimally thick, it could have some thickness, and this of course is the space-time of the Vaidya metric, and people have tried to see what kind of universalities do they imply. So a sample of possible universal behaviors of which come from this kind of metric can be is here, and what this graph shows is the behavior of the time-dependent entanglement entropy. So entanglement entropy, I believe most of us here know what that is. So this is in the context of ADS-CFT. This the CFT is supposed to live on the boundary, and this is of course the space-time of the CFT. And if you look at a certain time slice of this and consider a subregion of the space of the CFT, then you can think of quantum entanglement of that subregion to the rest of it. And one of the quantities that defines the properties of this entanglement is the entanglement entropy. Okay, I'll come to this, you know, more details of this thing. And the issue is, as you go up in time, okay, what is the structure of this quantum entanglement as a function of time? Okay, in particular, when you know, so this spacetime is something in which the past is ADS and the future is a black hole sitting inside ADS. So as you go from here to here, okay, you expect that the entanglement entropy should show some sort of properties of entanglement entropy in a thermal ensemble, and that's indeed what happens in this schematic diagram. So in this blue circle, okay, we show the approach to thermalization, and so there is also early time behavior which goes as t square up to some length scale. So I have taken this this schematics from paper by Hong Liu, and but there are reviews also and so on. So I'll say the you know, the literature after the talk. I didn't have the full extensive list here. Okay, so this is the region of approach to thermalization, and so then there's a so there are these two time scales. One is the saturation time scale, and this is this has been called in these papers as the local equilibration time scale. My interest here in this talk would be mainly in this, okay, in the late time behavior. And so here I have left this sort of disconnected. So the kind of information that is known again from studies of Vaidyametric is that if if one is talking about the you know, entangling region to be a sphere, then it is you know, the approach is like that. It's not like it's a smooth connection, and the connection is given by some power law with some non-trivial exponent. Okay, and in case of d equals 3, you know, it's this power law is modified by a log term. Okay, so this is how so this small d here is the space-time dimension of the conformal field theory. That was for an entangling region which was a sphere, and if you go to a strip, then it's you know, the linear behavior and the asymptotic behavior, you know, the saturation behavior, they don't quite from the holographic point of view, they don't seem to quite smoothly match. They seem to sort of be like two. In fact, in the geometry, that's what happens. There is a branch which goes off like this, and there is another branch which is the thermal thing. So it's like a first order phase transition from the point of view of the geometry. We'll study this one in more detail. So there is another class of space-times which has been studied extensively, and in particular in a you know, rather detailed paper by Maldersen and Hartmann in 2013, 12, I think. And the so here what is done is that so okay, I have well, all right. So there is also another class of spacetimes which are studied as well, which is the taking an eternal black hole, okay, which has two sides, and you start from some Hartle-Hawking state at time t equal to 0, okay, which is obtained by simply you know, functionally integrating the lower half of the space-time, which is replaced by a Euclidean geometry, and then just let it evolve. Okay. So the Hartle-Hawking procedure, it gives you some initial state. So I'm talking about the non-existent left half of this figure, But so in Maldaceno's paper in 2002 on the eternal black hole, as well as in the Maldaceno-Hartmann paper, it was shown that you can put an end of the world brane right down the middle of that diagram, and you know, in case you are not familiar with that work, just take this for a fact that if you start with a certain boundary state in a conformal field theory, so this is the boundary, okay, and do a Euclidean evolution for a quarter of a circle, okay, and then you arrive at some state here, okay, and then you evolve in Lorentzian time for the rest of the evolution, okay, according to the standard CFT Hamiltonian, and you can look at the time dependencies of that. The bulk story of this, the bulk story of this is it seems to be very time dependent. Is that there is a certain state which corresponds to a Hartle-Hawking state for this half space, and the rest of the space time is described by the future half of a black hole geometry. Okay. So that's what the story is. This is I have called this the Hartle-Hawking quench. This is a quench because you know, it's described by a time dependent. It's an instantaneous quench in the sense that in this part of the diagram, the Hamiltonian is time independent, and you start from a precise initial state. Okay. So some results here. This system, the CFT description of this has been studied for a long time, starting with Cardi and Calabrese in actually 2005, and then again in this paper of Maldaceno-Hartmann. So this graph, which I have mentioned here, okay, with a sharp discontinuity, with a sharp neck here, that is something that you obtain from gravity, and this is also the sort of approximately the picture that you get from the conformal field theory, okay, where so there's a linear behavior all the way from time t equal to 0 to this point, and the slope is given by the equilibrium entropy density of the thermal ensemble that it's going to attain eventually. And here, of course, the entanglement entropy of that region is given by the given by the thermal entropy density times the size of the interval. In this case, the region is here an interval because this is two-dimensional space-time, and space is one-dimensional. I am going to take space to be non-compact in throughout this talk. So this is the picture, but if you look at the CFT behavior closely, then you will actually see that in a small region around the neck, okay, there is actually some smooth joining between these two lines, and there is some exponential formula which joins these, and this will be one of our regions of interest here. Okay, and the precise rate of approach to this one, okay, or the departure from here, they have non-trivial information about the content of the theory, even the operator content of the theory, as well as some robust features of the initial state. Okay. This discontinuity is something that you get from gravity. In principle, you know, you can probably, even from the gravity end, you can try to explore this. Possibly, yeah. So I don't know whether this sort of a calculation has been done. Rob, do you know anything about?
Yeah, I was going to ask you quoted Cardi and Calabrese.
Yeah, Cardi and Calabrese, of course, find this behavior.
That has nothing to do with holography, then.
Oh, so the Malesina and Hartmann, the paper that sets this, that puts a sort of holographic setting for the cardiac calibration.
But
Yeah.
I'm just saying that the same result is just true of two-dimensional field theory or CFT.
Oh yeah, but I'm saying that this smooth joining of the two segments, okay, that is easy to obtain from the CFT, and what he's asking here is that whether it can be obtained from the gravity picture as well. Yeah, so. Yeah, hopefully I'll be able to say something about how exactly the smoothing is done. I mean, basically, reaching this point requires taking a certain limit in an operator product expansion. Okay, but the subleading operators, they are there. Okay, so if you are, so let me tell you what this region is. So the half width of this region is actually beta. Okay, where beta is the eventual temperature of the thermal ensemble that's here. So this Ts is actually half L, okay, which is the half the size of the interval. That's basically the light crossing speed of the light crossing time of the interval. This Ts is that, and this region, the size of this region is basically beta. So you have to be within that, T minus L by 2 has to be in fact significantly less than beta. Then you can get that. Hopefully, I will say under what are the terms in the operator product expansion which lead to such things. So we have looked at the first subleading term in the operator product expansion. This has been remarked in the Cardi-Calabrese paper as well as in the paper of Hartmann and Malesina, and it may also appear explicitly in some paper, but we have explicitly, in fact, there is a paper by Matt Hedrick which calculates the subleading thing in a slightly different context, but this thing can be okay. So this is one. So these are systems which correspond to instantaneous quench, as I said, because this part of the evolution, okay, is according to this part of the evolution in the CFT or in the bulk. It's according to some standard time independent CFT Hamiltonian with some non-trivial initial state, which is non-stationary initial state, which has been obtained here by some means, but the same kind of state could also be obtained by starting with a time dependent Hamiltonian, okay, putting some time dependent parameter in the, making some parameter in the Hamiltonian time dependent, and suddenly changing it from some value to something else. So there's a lot of story in that direction also, whether you suddenly change it or you change it slowly, and what is the effect on the dynamics, on the late time dynamics, on that sort of thing. And so I'm just going to mention it just in 1 or 2 slides, that you can do this, and for example, you can change this time dependent parameter in the Hamiltonian in such a way that there's a mass gap which becomes a function of time, and your external tuning of the parameter is such that this gap parameter goes through 0. Okay, so you have a parametric transition through a critical point, and then the universal features of in particular of the late time behavior, remember about the critical theory and the speed of quench. This goes under the general name of the Kibble-Zurek mechanism, in which if you are going from a disordered phase to an ordered phase in this fashion, the evolution is adiabatic in the beginning, and then it's when the gap is large enough, but when the gap is small, okay, then and in particular when you are approaching the critical point, then of course nothing can be adiabatic. Okay, so so you are sort of in the regime of a sudden time evolution, and the Kibble and Zurek, for example, had estimated the density of defects in the ordered phase, which has information about the speed of the quench and the dimensionality and the correlation length exponent. Okay, so and Z is the Lifshitz exponent of this theory. So there is some interesting story about how this slow quenches, if they are taken to the limit of the instantaneous quench, then whether the results that we know in that kind of direction, they nicely match to the results in for the instantaneous quench. And it appears that so I am not going to I just go to great details of this one, but for example, if your quench parameter is the coupling constant corresponding to a certain relevant deformation of the conformal field theory, okay, and then you have changed the coupling by an amount delta lambda over a time delta t, then the asymptotic one-point function is given by a behavior like this, which for 2 delta, which delta is the dimension of this operator, greater than d, clearly it looks like a divergent quantity in the limit of instantaneous quench, in which you let delta t go to infinity. Okay, and this limit is rather subtle to understand. Delta t going to infinity has to be really understood as delta t going to some value which corresponds to lattice cutoff, which has to be all brought in. I presume that Rob might talk about this work, so I'll. Oh, you won't. Okay. So anyway, I can discuss this. This is a very interesting development, and so anyway, but let me now carry on with my story of the initial universal behavior of this entanglement entropy thing. So when did I start?
You've got 40 minutes.
I got 40. Okay, good. All right. So this is so what are the questions that so I already said that so there is this t square and t and the constant this behavior. How universal are these features? Whether is it true of all systems? Certainly not, because this even the existence of an equilibration, okay, is not guaranteed for various systems. We know of the famous classic experiments of Fermi, Pasta, and Ulam, in which equilibration just doesn't happen in spite of anharmonic coupling between oscillators and so on. So this is not guaranteed, but here we will, of course, if you are starting from some, from a holographic situation which has the Vaidya metric in it, then you are guaranteed that your final bulk geometry is a black hole. So clearly this is guaranteed from that point of view. So all right. So now, however, then this thermalization behavior, what are the universal properties of that, and so on, and perhaps more importantly, quantitatively, what is this scale of the first kind of equilibration? What is this saturation scale? And what are the dimensional quantities that you have to supply here in order to write these functions? Okay, and these are all interesting questions. And how robust are these quantities? Okay, so yeah, this is what I said. So this is the plan of the talk. The rest of the talk. So I'll basically talk about instantaneous global quenches in a two-dimensional conformal field theory. So asymptotic time development of thermalization function. I'll explain what I mean by the thermalization function. This is a function which is built out of the reduced density matrix of a small region, okay. And if I can show that this reduced density matrix basically asymptotically approaches the reduced density matrix of a thermal ensemble, okay, then basically I have shown in effect that any string of local operators within that region will also approach, okay, the those operators in a thermal ensemble, thermal or whatever ensemble that is. And how this this study connects with the entanglement entropy studies, and as I said, the equal time correlations of local operators. And so yeah, so one interesting thing, if I don't have time to say it later on, is that if I consider local operators, this is very important. If I consider local operators, it doesn't matter even if I am looking at free field theory, okay. There is thermalization. Even in free field theory, there is thermalization, because it's local operators, and basically when we talk about a free field theory, like a free scalar field theory, okay, it's free in the sense that the modes are decoupled, etc., in terms of Fourier modes, in terms of momentum modes, okay, but not in terms of local operators. Like the elementary field phi of x, okay, it is coupled to the next one, okay. The various phi of x's, they are actually coupled by nearest neighbor coupling, and it's pretty much like in some of these some of the thermalization models like Caldera-Leggett and so on, coupled oscillators and so on. And as long as, so of course, if you say that, okay, do I expect equilibration of number operators corresponding to the momentum modes? No, certainly not. We don't expect such equilibration. But if I consider local operators, okay, then we do have this equilibration and nice exponents, etc., which come from those studies. Okay, so excuse me. And so that's part one, and part two will be the comparison of this thing with the formation of higher spin. So here what I forgot to mention here is that the stuff that is known, perhaps not completely derived, is about instantaneous quenches in conformal field theories, where only the Hamiltonian is the conserved quantity. But if you have conserved charges, including an infinite number of conserved charges, okay, then the story of these things is new, and that we have also in fact derived some of the thermalization properties even with just the one conserved charge in some detail, but this part will be new. So the calculation of thermalization rates as a function of conserved charges. And what is this ensemble? Okay, so because there are so many conserved charges, the ensemble is not a thermal ensemble. It's not a standard Boltzmann thermal ensemble, but it's an ensemble with chemical potentials, and in particular, if there are infinite number of conserved charges, it's an ensemble with infinite number of chemical potentials, which has been called the generalized Gibbs ensemble. It's called the GGE, and the so you might ask then the question that how does so a normal thermal ensemble is described by a black hole, okay. This GGE, which has an infinite number of conserved charges and therefore an infinite number of chemical potentials, what is it described by in the bulk? So in three-dimensional geometries, okay, there seems to be a ready answer given by higher spin black hole studies, is that higher spin black holes, okay, have an infinite number of conserved charges and infinite number of chemical potentials. So perhaps, so this is something that I had conjectured in a paper with Takeshi Morita about a couple of years back, that this GG, this generalized Gibbs ensemble, which we had found in some matrix model studies that might correspond to higher spin black holes. Now we have proofs that so far as the equilibrium property is concerned, okay, This actually has already been anticipated in a paper by Krauss and Perlmutter and so on, who have studied equilibrium properties of these spin black holes. We compute the same objects from a conformal field theory and see that they match. But the other interesting thing that follows is that this approach to equilibrium is governed by an exponent, okay, which we can compute from this conformal field theories by using our methods, and that matches with the quasi-normal frequency calculation of these higher spin black holes. So, we have matched just the first quasi-normal frequency, which is called mu3. That is the quasi-normal frequency of a scalar field when there is a coupling of the scalar field to a background higher spin field, spin 3 field. Okay, so that quasi-normal frequency have, in fact, there is a paper by Narayan et al. Which computes quasi-normal, which gives an exact black hole metric calculation for higher spin black holes. So, we have taken their result for the for just the coupling to. So, this is the quasi-normal frequency of a scalar field in the presence of a spin 3 black hole. But in principle, we are doing the calculation for higher chemical potentials now to see a match. Okay, so I'll soon go to the blackboard. So, this is the beginning. That so what we'll discuss is the instantaneous global quenches in a two-dimensional conformal field theory. So, space will be non-compact, as I said. And what do I mean by this? So, first of all, what will be our focus to keep in mind, not to get bogged down by the calculation, is that so we have 2D conformal field theory. Okay, we don't have a mass scale. We are sitting at the fixed point, and so various scales, which govern the approach to thermalization and so on. Where can they come from? It can come from the preparation of the initial state that might have some scale associated with it, and of course, the choice of the observable, okay, whose time development is being studied. That can also have a scale in it. So, a class of states which has been extensively studied by Cardi and Calabrese et al. Is this kind of state. So, you start with a conformal boundary state, okay, at time t equal to 0. So, this is the well. So, let me just go up and say where in our. So, there is a state. So, we would like to define what the state here is, okay, what the state here is. And so, ideally, if I think of this the time t equal to 0 itself as a boundary, okay, of my conformal field theory, remember that the space is a direction which is coming out of this diagram. So, I might want to put a boundary state here, okay, a conformal boundary state which ensures the condition that stress energy tensor does not flow out, etc., etc. These states could do the job, and that is what you might think that these states might do the job. So, that is called a boundary state, okay, but that is not what I am taking here. Okay. I have put here some ultraviolet cutoff, okay, applied to the boundary state. The reason being that these boundary states are actually not legal quantum states in a Hilbert space, because these are not normalizable. Okay. For example, in a C equal to 1 free scalar field theory, a Dirichlet boundary state looks like this. As you can see, there is no damping factor for the various modes, okay, and all modes, where this n is the momentum label, and it sort of is summed over all possible momentum modes. And if you compute the norm of this boundary state, you can immediately see that it's infinity. So, somehow you have to damp out the UV modes, the UV momenta coming from here, and this is clearly one way of a very traditional classical way of doing it is to put a cutoff like this on the energy. So, this cutoff kappa that introduces a scale in the initial wave function. What does the scale do? Basically, it produces a damping factor on the occupation number of high momentum modes. Okay. And how high is high? So, when kappa times n is 1, okay, then this well, kappa times n over L is 1, then this n of the occupation number of that momentum mode, okay, cannot be it has to be less than 1, okay, which means those modes are not there. Okay. So, that gives you a notion of UV cutoff on the momentum, and that is essentially given by 1 over kappa. Okay. So, from this point of view, you can carry on a little bit to see how the various quantities like energy density of that. I am talking about a non-local initial state here. So, I should talk about energy density rather than energy, and the energy density is given by the scale square, and because energy density has the dimension of mass square in these things, and you can compute some few more properties of the initial state, and you may want to guess that if such a state attains equilibrium, okay, then maybe the equilibrium will be described by that energy density and the corresponding temperature and so on. Okay. So, this however, there is a way of understanding this cutoff which was introduced by Cardi and Calabrese in 2005. In fact, that is much more elegant than all of this, is that you think of this kappa, okay, as a Euclidean time evolution, as an imaginary time evolution, okay, and just that point of view immediately makes all the calculations very simple by using some tricks of conformal field theory. In particular, for example, suppose you take, so what is my initial state now? Okay, I have called this psi naught later on. My initial state is this, okay, which is starting from a boundary state. It has a little bit of excuse me. So, I start from a boundary state. This is my imaginary time direction, okay, and so I do an evolution by some imaginary time kappa, and I reach here. This is my time slice t equal to 0, and I insert an operator here, and if I am interested in computing an expectation value, then I do the same thing from starting from up here and coming this way. So, this expectation value then is given by a functional integral, okay, in which there are these two boundaries, and there is a 2 kappa length okay, of a strip in the middle. So, this is just a computation of a 1-point function on a strip, and that of course can be obtained by standard methods. So, and that this thing was about this was about the the expectation value at the time. This is space, and I also put the operator at 0 at time t equal to 0. But you can allow for a complex time in which the the real time is some other direction. This is the imaginary time, and the real time in some other direction. And using this analytic continuation tricks, you can compute the time dependent operators, okay, time dependent operators that way, and so let me just tell you the results is that the system attains equilibrium, which is thermal, and the relation between kappa and the temperature of the final equilibrium is given by kappa equal to beta over 4. This was shown by Calabrese and Cardi, and the large time behavior of 1-point functions, okay, is given by some exponential formula like that. The infinite time behavior in this case is actually 0, because the 1-point function, okay, this is the 1-point function in a thermal ensemble. Okay. So, the 1 point function in a thermal ensemble is actually 0, okay, of these operators. These are scaling fields, and essentially these 1 point functions become like 1 point functions on a complex plane. Okay. And 1 point functions on a complex plane by conformal properties, they are all 0. Okay. But the interesting thing here is to find out the exponent, okay, and the exponent is given by 4 pi h k over beta, where k is a certain label of this primary field in the conformal field theory that appears, and the thermalization rate of the reduced density matrix. So, this I am going to explain now in some detail, which is this way, which is given by again a similar exponential like this, where this gamma is a particular exponent which characterizes the minimum, the most relevant primary field in the conformal field theory, okay, which has the minimum scaling dimension. Okay. So, that's what it is. You take that field, take the, sorry, I forgot to mention that this h is the conformal dimension of primary fields in our theory, and so it's given by 4 pi h m over beta. So, this is something, this is some result which has appeared in a paper by Cardi in April this year, and in our paper we have given a proof of this, and so this is the, okay, so so these are the 3 results which you can. Now, the interesting thing is that suppose that, so that cutoff was very convenient. That cutoff was very convenient because that cutoff allowed an interpretation in terms of imaginary time evolution. Okay. Suppose, however, now you put in a cutoff which has not only the Hamiltonian, but some other conserved charge. In particular, okay, suppose my conformal field theory has higher conserved charges like the W's, okay, such as this. So, now I have a kappa 1 h and a kappa 2 W3. This does not have the interpretation of an imaginary time evolution anymore. Okay. So, what is going to be the behavior of, this second line of reasoning which was introduced by Cardi by using these beautiful geometric formulas, that does not seem to work, unless somebody finds even some geometric property of W, the W evolution, okay, is also. So, we looked a lot in the literature, okay, whether a combined H and W evolution, okay, has some geometry, not perhaps in terms of the standard simple Riemannian geometry, the strips and things, but maybe higher genus Riemann surface and so on. There are some mumblings like that in the mathematical literature, but we couldn't quite get it. So, anyway, what we do as a result is like what anybody in the audience would do perhaps, is to bring it down. Okay. So, think of this this as perturbation, but fortunately we were able to resum, okay, this perturbation series to put it back in the exponent, and we get as a, so you can ignore all this. Here I am just trying to sort of say that the first line of reasoning which tried to find some cutoff, okay, of the momentum, the UV cutoff of the momentum, that can still work. Actually, this is the momentum cutoff that you get in terms of kappa 1, kappa 2. So, you can try to carry on a little bit about, so this is what, so you have to put this equal to 1, okay, in order to find out which occupation numbers do not appear anymore. You say, well, this, if this is equal to 1, well, divided by L, if that thing is equal to 1, then you have reached the UV cutoff of the momentum, and from that point of view, and so the result is going to be that this kappa 1 is again going to be beta over 4. So, there is thermalization, and this kappa 2 is going to be the chemical potential of W3 divided by 4. That is what is going to be. Okay. So, this kappa 1 is going to be beta over 4, kappa 2 is going to be mu 3 over 4. Okay. That is what we find, and the thermalization exponents here, okay, they have this one or this one, they have you know, basically this kind of calculation, what we first found was that, well, up to this thermal exponent, the purely thermal exponent we can get in the exponent as an exponential form. Then is some 1 plus mu square, etc., etc., etc. Okay. But somehow we are able to resum that resum the series to put it back in the exponential like that, so that now we have an expression for gamma gamma in terms of beta and those mu's. Okay. So okay, so that's what it is, and maybe in view of, oh, my battery is dead also anyway. So okay, anyway, now I'll go to the blackboard. Can somebody do something about this? Yeah. Yes.
Along the same lines of what you had for the stress tensor,
Right.
like you said that it's evolution, I mean, in terms of imaginary time. So can this be thought of some imaginary spin 3 chemical potential? I mean, because you're getting some similar answer in terms of the.
But I want a functional integral. Excuse me. I want a functional integral in terms of some geometry, which then so what was Cardy's technique? So maybe I should say that a little bit, what Cardy's technique was. If you can identify this kappa as an imaginary time evolution, okay, then it becomes a problem on the strip. Okay. This strip thing, then you can conformally map to the plane. Okay. Everybody only does in two-dimensional conformal field theory, the final calculations are always done on the plane. Okay. So if you take this point of view that it is some kind of evolution in chemical potential, that does not lead to this kind of a geometry. That if it so happened that okay, that I have some complicated Riemann surface or something in which there are various cycles along which I could evolve. Okay. So beta evolves according to something, and mu evolves in some other place, and so on and so forth. Okay. It's almost there in some math literature, but I'm not sure. Okay. Then of course all this calculation would be very, very simple. You just take that Riemann surface, map it to the plane, and then the information about beta and mu are in the map. Okay. And you do some calculation on the. So let me just in view of the sure, yes. We tried that. No, it's true. That was not useful in doing the calculation, because I don't know the partition function or one-point functions in the presence of those flat gauge fields also. Okay. So Justin is smiling. He has a lot of experience in this thing, of course. Right. So in view of the sure fact that I'm not going to finish, so let me just let me 10 minutes. Okay. So let me just tell you the result. In order to say the result, I have to just introduce one really amazing. I mean, it's a beautiful function which was introduced in this paper of Cardy in April this year. Which I don't remember what he calls. He doesn't call it anything at all, but I think it deserves a name. We call it the thermalization function for a region A. So what is that? So suppose that we have, let me say it in general now. This is space of a certain field theory. This is the region A, and the rest of it is region B. As we know, we can compute rho of A as trace of over the Hilbert space of B. I'm assuming that the total Hilbert space has the product structure, etc., and not gauge theories and so on. So and here I can have a pure state like this. So this is the reduced density matrix of a pure state. If this state is dynamical, okay, this state is dynamical, then it will have some thing like this. Let me typically these states are normalized in such a way, excuse me, that this is equal to 1, but the trace here is over. This is clear already from the definition, but I am going to introduce another notion which is a square normalized, reduced density matrix, which is nothing but this this divided by trace of rho a t whole square and square root. Okay. This is a square normalized density matrix, and I am going to now define this thermalization function, and let me do the same thing for a thermal ensemble in which I replace this object. So, let me also do rho of beta, which is so I take the so I had taken this whole system in a pure state first, okay, psi of t. Now I am replacing this psi of t, this pure state density matrix by, and I am going to sort of more generally mu1, w1, etc., whatever. So let me for the moment let me do this. Okay, so this is I should call it rho a of beta. Okay, and similarly I define this object, okay, and which is a square normalized thing. Then Kari defines this thermalization function which he calls I of t, that is given by the trace of rho hat a t and rho hat a beta. Okay. And now suppose that you can show such things, that I as t goes to infinity is equal to 1. Suppose you can show this, and then I will also tell you about the approach of I to 1. If you can do that, then this trace of this rho hat fellows, you can think of that as a scalar product. Okay. The operators can be thought of as matrices, and the trace can be thought of as a scalar product. So, and this can be thought of as a unit vector with respect to that scalar product. Okay. So, this is like then, just to make that point precise, this is easy to see. This is a standard thing. In the, matrices can be thought of as vector spaces, and the trace can be thought of as a scalar product, and so on. If this is true, then what is happening is that one unit vector dotted with another unit vector is going to 1, which by Cauchy-Schwarz inequality can only mean that this unit vector is going to that one. Everybody with me here? One time dependent unit vector at time t going to infinity has one dot product with this one. So, basically what it means is that infinity dot is equal to 1. Okay. That can mean that these vectors are either collinear or they are anti-collinear. Okay. But the anti-collinear option is not there here, okay, because of the properties of density matrix. So, therefore, it says that rho hat of t as time t goes to infinity, okay, is it goes to rho a of beta, which means that the original rho, that is a trivial statement, rho a of beta, okay, which is the standard normalized rho, because they are square. If they if this guy goes to this guy, okay, then this has to go to that. All right, what does it mean? That means then that if you put any number of operators here inside, okay, then the O1, O2, On, whatever, all of them inside region A, their trace with respect to the Hilbert space of A now, rho A of T, is clearly becoming thermal, provided all of these are in the region in the region A, right. If the reduced density matrix of a certain region itself goes to a thermal reduced density matrix of a thermal state, this means the following, that suppose I take all the operators O1, O2 up to On in the region A and I do this exercise, okay, that is O1, O2, On e to the power minus beta, okay, it's rho beta, rho A of beta, okay. But because these are only local objects, okay, this actually gets elevated to the full Hilbert space. This becomes O1, O2, On e to the power minus beta h. That is easy to see because these fellows don't have any leg in B. Okay. So therefore, this becomes that. Okay, because when I do the tracing, I can easily trace over B, and that affects only the e to the power minus beta h part, and it does not affect these guys. So that this becomes that. Okay, and it just so the right hand side is the thermal expectation value in the full ensemble, and this is also by the same logic. It becomes trace of O1, On, psi psi, which is the same thing as psi O1, On. Okay, this the time dependent fellow. Right, this is what it is. Reduced density matrix from the thermal ensemble in A, right, right. H is the full Hamiltonian of the full system. Yeah.
Okay, so you're just saying that, I mean, if this subsystem A has H, so it must be true for all the subsystems, right?
It must be true for any particular subsystem, but there is a dependence of this rate of rate of equilibration and so on and so forth on A, which I have not explicitly written. This I A of T. Okay, so there is a dependence on that that thing. Okay, so now let me. How much time do I have? 5 minutes. Okay. Okay, results. Right. So okay. So now, so now this I of T, okay, has a structure like this, e to the power 2 gamma of T. And so where as I said, gamma is given by 4 pi h m over beta. This result has already appeared in Cardy's paper in April, and as a result, of course, it means that all local and yeah. So actually, let me say that let me put. So this is, of course, okay. So we can prove this at large times. Okay, large times means that T over beta. So this is what Cardy's claim is, and but if L is small, okay, if L is small, then essentially you can forget about the L. And we are able to derive this thing in the regime in which we use something called a short interval expansion, okay, in which this actually gets brought, yeah. So gamma has a 1 over beta in it, okay. So this actually gets brought down to this thing, and okay, I didn't have time to say how the so let me just say it very quickly. What oh, L is the size. So now A is an interval because space is one dimensional, and L is that the length of this interval. Okay, we are talking about a single interval now. Okay, now so let me just try to match this with entanglement and entropy. So as I said that Cardy has transformed the problem in case of a pure beta, no mu. Okay, Cardy has transformed this problem to problem of or like one-point functions have become this problem. It's a one-point function on a strip. Okay, but if you consider entanglement entropy, let me say it without proof, is that it becomes, let's say this is the interval. Okay, it becomes a problem of a two-point function on the strip, in which at the two ends of this interval here, okay, you put two twist operators. Okay, so and then a conformal map. Where are the dusters? Okay, so the conformal map makes this thing into, so first of all, time evolution from one boundary to another boundary is mapped into the bottom boundary becomes the right half plane, and the time evolution, this one, okay, becomes the angular evolution. So the other boundary comes here. So both these boundaries are joined here, okay, on the boundary of the upper half plane. And these 2 points, they are somewhere here, okay, something or here, etc., whatever. Now, such calculations in which there are two fields sitting at these 2 points, and then there is a boundary of the upper half plane, can be computed by a mirror method, okay, in which this 2-point function actually becomes a 4-point function, in which you put the mirror images of these objects here. Okay. So there are 4-point functions which are involved here. In computing this and what happens in the large time limit is that both of these points, okay, they just come very close, okay, because of the complex time, etc., which I cannot now tell you. So both of these points, okay, they just come very close to the real axis, and their image points, okay, which are not now the complex conjugates anymore, they go to very far down, okay, like that. And then the calculation that was done in Maldasen and Hartmann's paper is something in which they just took only the leading operator product expansion, or in Calabrese's calculation, they had taken only the leading operator product expansion of these two fields which are sitting here. Okay. If you take the subleading term, okay, then you see that you get these exponents in the entanglement entropy calculation. So the entanglement entropy calculation can be connected to this thing, to the calculation of the I of t. What I should say here is that this behavior says that rho a of t, it actually goes to rho a of beta, okay, into 1 minus, let me ignore this for the moment for short intervals, like that. And then, so this is one unit vector, it goes to another unit vector, and then there is a difference vector, which you can also make into a unit vector, okay, times some dependence. This is the bounded time dependence here, and there is some e to the power minus gamma t. This is the full behavior of the reduced density matrix itself, and like that. Using this,
so this calculation is being done in Euclidean signature, right? These are Euclidean.
That's right. This is the Euclidean signatures.
Time evolution, shouldn't
Good.
In that sense, you should be getting conformal dimension.
Good, 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 good. So here it is like, let's say W is given by some sigma plus I tau. Okay, this is Euclidean. Let me say that I am doing a Euclidean field theory on the strip. Then what I do is to use this exponential map, which is 2 pi over beta W. Okay. This fellow here is sigma plus I tau. Now suppose that I make this tau into tau 1 plus I tau 2. It turns out that I can keep the z and z bar independent in my calculations. Z and z bars don't get mixed up in my calculations. So as a result, I have independent analytic continuation in z and in z bar, which allows me to do this trick. Here, so far as z is concerned, you see tau 2, which is the imaginary part of the Euclidean tau, which means is the real time, that gets added on to sigma. And in z, it's sorry, excuse me, in z bar, it was e to the power 2 pi sigma minus I tau, okay, and this you write as tau 1 plus, wherever tau appears, okay, that's viewed as a real tau, okay, but now it is like this, okay, like that. Now you can see that it appears as e to the power minus tau 2 here, and it appears as e to the power minus tau 2 here. So, and tau 2 is actually t, it's actually t. So as a result, this shrinking down, so this has an overall I in it, and it shrinks down to the real axis. So in all our calculations, this geometry is very important, okay. And since I'm really up for time, let me tell you how. So this is the result that we use to say that, well, you can take trace rho log rho. Once I know what the behavior of rho itself, so from the behavior of I of t, I can go to the behavior of rho a of t. Irrespective of the behavior of this unknown unit vector here, I can determine, okay, how the entanglement entropy coming from here and the entanglement entropy coming from here, they approach each other. And that indeed corresponds to, we have checked this explicitly, corresponds to going to the next subleading operator in the operator product expansion here of these two object points, okay.
Subleading in the conformal dimension, not in the twist.
Subleading in, actually it is subleading in some cross ratio, but that subleading in is in some x, so it's like O1 of x, O2 of 0 gives you the first term, is some kind of x to the power h, and then the next term is x to the power h plus something, and this x is e to the power minus t. So it's subleading in at large time. So it's subleading at large times, but now you see, I have probably rubbed it off. Here it is. So you go by an amount. Remember that I have claimed that kappa thing, okay, the imaginary time evolution kappa, is to be identified with beta over 4. If this is beta over 4 and this is beta over 4, the whole thing is beta over 2, okay. So therefore the total time evolution from here to here must be beta over 2. So from here to here, therefore, the angular Hamiltonian, okay, traverses beta over 2. Now if you make this upper half plane calculation into a calculation on the plane, okay, there the angular Hamiltonian corresponds to, it traverses beta over 2 here and a beta over 2 here, so that's a full beta, okay. So that then is a thermal ensemble with respect to the angular Hamiltonian, okay. So calculations on the strip can be converted into calculations on the of the thermal ensemble, okay, in which the Hamiltonian is taken to be the angular Hamiltonian. Okay, so now, so there's a lot of technology here about how to actually prove this, and in any case, I think that was probably not going to be too illuminating. But let me just tell you the one little thing, that when we have the the other guys, so if you have e to the power minus beta over 4h minus mu over 4w acting on the boundary state, if this is my quench state, if this is my state here, okay, then first of all, this identification is correct. That is to say, if this was kappa 1 and if this is kappa 2, then our eventual thermal ensemble is going to obey this identification. So indeed, it corresponds to a thermal, and when I say mu w, there can be any number of them. Okay, there can be any number of them. And so this identification is correct. This we can show rigorously, not in a perturbation series in mu. Okay. In order to compute objects like these, okay, we have to bring them down. Okay. Bringing them down means that now whatever whatever else we want to do, let's say there are twist operators and so on and so forth, but in addition there are lots of these W insertions. Okay. Lots of W insertions which corresponds to, but these are conserved charges. So this corresponds to putting lots of contours of integral. For us, space is like this, these radial things. Okay. So let's say 2 W insertions correspond to 2 W contours. Okay. Then you can do some jugglery using Cauchy's residue theorem, etc., to resum, okay, this infinite number of W insertions. Okay. So that eventually you get some result like this, that is HM here plus essentially now I am dropping the constants, okay, it's mu3 q3, okay, where this refers to the conformal dimension of the most relevant operator, this refers to the W3 charge of the most relevant operator, and with constants here which we have determined. Okay. So this corresponds to this thermalization exponent in the presence of mu3s. Okay. Here order mu squared terms, okay, we are not able to compute yet by our methods, but as I said that our calculation, okay, starts with this and then it has 1 plus everything other than this 8 pi h m t over beta. Okay, the whole thing was mu square, etc., etc. Okay, but we can compute the coefficients here. Okay, so there is mu t, there's mu square t square, etc., etc. Okay, they are exactly of the right kind, so that it goes up in the exponent. Okay, and you get some delta gamma of t, and that gives you this correction. Okay, so gamma is equal to 4 pi over beta hm plus blah blah blah. Okay, and this part exactly matches with the quasi-normal frequency calculation of the higher spin black hole that was done by Narayan et al. Okay, okay, I'm done. Thanks.
There'll be a coffee break here now, and then we'll reconvene in 15 minutes for the next 15-20 minutes, the next session. Okay, and then we can continue discussing